This is Lab 3. The purpose of this lab is to find the unknown mass of a black hole by analyzing the motion of a star and to find the net force on that star. The initial data I retrieved from WebAssign is as follows. The mass of my star is 5.4044 times 10 to the 27th kilograms. The time step is 86,400 seconds, or 1 day, and the black hole is at position -1 times 10 to the 10th meters in the x direction, -4 times 10 to the 10th meters in the y direction, and 0 meters in the z direction. From this data and through the use of the VPython code, I determined the mass of the black hole to be 4.577 times 10 to the 31st kilograms. So the way that I calculated this mass was through the use of Newton's law of gravitation. The equation in which the gravitational force on the star by the black hole is the gravitational constant, g, times the mass of the star, times the mass of the black hole, all divided by the square of the magnitude of the position vector of the star relative to the black hole. And when this equation is rearranged, m2, or the mass of the black hole, can be found. This other equation, F net equals F parallel plus F perpendicular, will also be used later in this lab. As you see in this first bit of code, I have my star mass written in 5.4044 e to the 27th, delta t, which is 86,400 seconds, and the initial time of t equals 0 seconds. And here is the while loop in my code. As you can see, I have included the initial and final velocities and momentums, as well as the change in velocities and momentums. I have F net equal to dp dt, which is in turn equal to the change in momentum over the change in time, delta p over delta t. Because of this, I can set my F net parallel equal to my dp dt parallel, and my F net perpendicular equal to my dp dp perpendicular. In this final section of code, I have the equation I used to solve for the mass of the black hole, as you can see here. And finally, I had to set the 3 different arrows to run in my code. Initially, the arrows were way too large and would not even fit on the screen, so I needed to adjust my arrow scale to make sure I fit everything in correctly. So now if I run my code, you can observe the motion of the star going around the black hole. As you can see there, the black arrow represents F net parallel, the blue arrow represents F net perpendicular, and the yellow arrow represents F net, which is pointing directly at the black hole. And you can see here where the mass of the black hole is determined through the use of this code, which is once again 4.577 e to the 31st. So what does it all mean? How is the net force, which is equal to F parallel plus F perpendicular, different from the change in momentum over the change in time, dp dt, which is equal to dp parallel plus dp dt perpendicular? The difference is that the change in momentum over the change in time, dp dt, can actually be observed, whereas the force cannot be observed. This is because the net force is all the forces acting on the system together, while dp dt is only the change in momentum throughout the time that the system is running. So what if the black hole, whose mass I found, was removed and a different black hole is placed in the same location? Could you tell the difference if the motion of the observed star remains unchanged and is affected only by the gravitational force of the new black hole? No. Since the motion of the star does not change, you could not tell the difference because this means that all factors, including the net force in the star, remains the same as well. That is my Lab 3 presentation, and thank you for watching.